Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be solving this question which says that show that 2017 divides 1 plus the integral from 0 to 1 of ln x to the power 2016 dx. So in such questions it's preferable to always begin with the unknowns. So first of all, because we know 1, okay, so we need to get the value of this and then we see what we can do later. All right, so I start by I'm going to let maybe I of n, or sorry, I to be equal to, let me just put e. I let e to be equal to the integral from that integral, okay. So let e equal to that integral. Now you realize that this power is too big, so I will start by getting a general form. So maybe let me just consider integral I of n equal to integral from 0 to 1 of ln x all that to the power n. If I am able to get this integral in terms of n, I'll just replace n with 2016 so that I get my e, okay, because e is just I of 2016. So our e is simply I of 2016. All right, so to do this we go via integration by parts, where we can let u to be a function we can easily differentiate. So I let u to be ln x to the power n. I differentiate both sides, I get du. I drop the power, I differentiate the ln, I have 1 over x, then I multiply it with ln x to the power n minus 1 dx. So if I want to write it, I'm going to say n divided by x times ln x raised to the power n minus 1 dx. Now I'm going to have my dv to be equal to dx, which is the remaining part of the integral. I'm going to integrate both sides and I'm going to get v equal to x. Now we now use the integration by parts formula, which says that our I of n will be equal to uv, so uv from 0 to 1 minus the integral from 0 to 1 of v du. So minus the integral from 0 to 1 of v du. So if we fit in, we are going to have our u is simply ln x to the power n, ln x raised to the power n, that's our u. Then our v is simply x, so I can just put the x outside here. Now I need to put my bounds from 0 to 1, then minus the integral, so minus the integral from 0 to 1 minus the integral from 0 to 1 of v du. Now what is my v? My v is x. What is my du? This is my du, everything here, so I just attach it to it. Okay, so we can just cancel. I can put the nx in the numerator. All right, now you realize that this function ln x is not defined at 0. So basically, in fact, this integral is an improper integral, so we needed to take a limit of a certain proper integral. So I'm just going to write this guy here as the limit. So I of n is equal to, since it is an improper integral, I will have the limit. Where is that limit? The limit as maybe a certain t tends, sorry, the limit as t tends to 0 from above, actually, of x times the ln of x raised to the power n, okay, from 0 to t, all right, no, from t to 1, then minus. Now this part here is going to simplify to something. This part, you have the x will cancel and we are going to be left with n, okay, we can take n out of the integral since it's a constant, it does not depend on x, and then we have this. All right, so let us just get I of n to be equal to, now I'm first of all going to fit my bounds before I find the limit. So I have the limit as t tends to 0 from above. Now if I replace 1, okay, I'm going to have the upper bound to be 0 because ln 1 is 0. If I replace t, I'm going to have t times the ln of t times the ln of t, all that raised to the power n. That's what I have. Then minus n. Now this portion of the integral is just I of n minus 1, since our I of n was the integral from 0 to 1 of ln x to the n. So the integral from 0 to 1 of ln x to the n minus 1 is I of n minus 1. Alright, so let's see what we have. Now this limit gives us 0 clearly, okay, because t is tending to 0, so the limit gives us 0. So it means that that first portion wipes out. So it therefore means that our I of n is simply equal to negative n times I of n minus 1. If you look at I of n as a sequence, right, you're basically going to see that if we take some steps behind, if we look for I of n minus 1, it's going to give us, if I of n is equal to negative times n into n minus 1, you realize that I of n minus 1, we see put a negative, we replace our n here, right, we replace n here with n minus 1, so we have n minus 1 times I of n minus 2. So what about I of n minus 2? I of n minus 2, we have the negative sign there, we have n minus 2 times I of n minus 3, and so on and so forth. So let's start fitting back. So I have the negative sign out there, I have my n, okay, I have my n. Now in a place of I of n minus 1, which is this, I'm going to replace it with everything here. You see, I'm going to replace it with everything here. Now in a place of I of n minus 2, okay, remember that this is still a negative 1, so it multiplies with this negative 1 to give us negative 1 all squared. So I'm just going to remove this and I put n minus 1 times I of n minus 2. Okay, now what is I of n minus 2? This is I of n minus 2. Here is I of n minus 2. If I remove this and I attach this negative sign multiplies with this one, you have all cube, okay, and I of n minus 3, and so on and so forth. So what can we generate? We realize that or we can just conjecture or deduce that our I of n is simply equal to, you clearly see that when it is 3 here, okay, when it is 3, the power of negative 1 is also 3. So it means that if it is n, we have negative 1 raised to the power n. Now you see that n times n minus 1 times n minus 2 times n minus 3 right down till 3 times 2 times 1 just defines n factorial. Alright, so it means that this is our I of n. So we can now get E. Our E is equal to I of 2016, which is simply negative 1 raised to the power 2016 times 2000 times 2016 factorial. But 2016 is even, so when you raise negative 1 to that power, you get 1, so it gives you 2016 factorial. So we have gotten our E. Now what about 1 plus E? So 1 plus E, so 1 plus this integral becomes 1 plus 2016 factorial. Now we have to prove that we are left to show that 2017 divides 1 plus 2016 factorial. Now let us recall a certain theorem called the Wilson's theorem. So recall, it says that if P is prime, okay, if P is a prime number, if P is prime, then P divide p minus 1 all factorial plus 1. Alright, now 2017 is clearly a prime number. It has only two positive divisors, 1 and itself. So it therefore means that we can say, since 2017 is prime, then from the Wilson's theorem we have that 2017 should divide 2017 minus 1 or that factorial plus 1. So hence we say 2017 divides 2016 factorial plus 1 as required. So we have proven that 2017 divides this integral. Alright, thank you guys for watching, and see you in the next video. If you have any question, ask. This is very complicated to actually come out with -1 to the n times n factorial. So do the recursion very well and you're going to see what I'm talking about. Look at I of n minus 3. If you want to get it, we are going to replace -1 there times, we replace our n, because to get I of n minus 3 I need to replace n here with n minus 3 as well. I'm replacing n with n minus 3. This becomes n minus 4. So you have n minus 3 times I of n minus 4. Okay, now the -1 leaves this position and increases the power of this -1 by 4, and you have I of n minus 4, and so on and so forth. And you should also know that n factorial is simply equal to n times n minus 1 times n minus 2 times n minus 3 right down till 3 times 2 times 1. So basically we just identify this guy here as n factorial. Now you realize that -1 to the power -1, the power of -1 is just increasing. Okay, the power of -1 is just increasing. So we have done 4 recursions. That's why we have 1, 2, 3, 4. That's why you see the power is 4. It means if we do n recursions, the power will become n. So that's how I got it. Alright, thank you guys for watching once more. See you in the next video. Like the video, share the video with your friends, and subscribe to the channel.